Hello everybody, I am Zachariah Peterson. Welcome back to my channel. Today I'm going to be answering a viewer question about vias in SMD pads in PCB design. Should you do it? Should you do it in bottom terminated components or in any other type of component? We're going to take a look at that viewer question. We'll jump into some examples in Altium Designer, and I'm going to show you some data from the IPC High Density Packaging user group that illustrates what can go wrong if you use a via in pad. Let's go ahead and get started. So before we look at some reliability data for via in pad, let's take a look at that viewer question. This viewer question comes from one of our design review videos entitled ESP32 Design Overkill. You guys know how much I have a love-hate relationship with ESP32. And this question comes from WoWoWeeWa2203. Nice username. Hi Zach, I want to ask, given the manufacturing capabilities nowadays, is it still suggested to route out vias from pads, or is it fine with via in pad now? Because most PCB manufacturers in general will finish off the PCB by covering the via through holes. In addition, packages are just getting harder and harder to completely fan out with smaller pitch. Our team has no choice but to use more expensive blind and buried vias now due to the package on LPDDR5s. There are a few different dimensions to this question. So first of all, most PCB manufacturers will leave your vias untented if you don't tell them to tent the vias. If your PCB manufacturer is taking your design that doesn't have tented vias and is just tenting them anyways, you need to find a new manufacturer. Your manufacturer should produce the board based on the data that you give them, not the data that they want to put into the board. The second point I would like to note regards the manufacturing capabilities for via in pad. The manufacturing capabilities have not been a problem for quite a long time. Now, manufacturers will recommend to people to not put the vias in pad, I think because a lot of people will just put via in pad and then they won't think about whether or not they need to have it plated and filled or capped. So if you are going to use via in pad, you need to make sure that you use it correctly. If you put vias under SMD pads, make sure that you specify a conductive or non-conductive fill, and then specify whether you need it planed over and planarized. Now, if you are using a high density BGA, of course, you're gonna find yourself in a position where you have no choice but to use via in pad. And that means you are going to have to specify filling and capping and plating over. What I wanna do now is hop into Altium. We can take a look at some designs that need via in pad. We'll see how to use it correctly, and then we'll take a look at some reliability data for via in pad so you can understand the risks of using via in pad in your designs. Now, the first design that I want to look at is our Ethernet switch project that we did for Altium Academy. And you can see in this Ethernet switch, we have three BGA components. We have the main Ethernet switch controller here on U1. We then have an expansion PHY over here on U3, and then U5 is a DRAM chip. So if we put this into 2D, we can zoom in and we can see what type of design we're working with here. So this is a design that does not require via in pad. Now, we could use via in pad if we wanted, and we could use blind and buried vias if we wanted to, but in this design, we're not required to. The reason for that is, of course, if we just take a look at the pitch on these pads, if I can get my snap to work correctly, if we just take a look at the pitch on these pads, you'll see here that the pitch is 1 millimeter. And of course, we're able to fit an 8 mil or a 10 mil via right here in between these pads, as you can see right here on this selected via. Even if we go over to this a little bit denser BGA for this DRAM chip, you'll see here that if I measure the spacing between the pads on the DRAM chip, this is 0.8 millimeters, and the pad and via that we have for this fan out is an 8 mil drill with a 16 mil pad. So again, we're still able to use the dog bone fan out on these BGAs, even when we get down below 1 millimeter pitch. Now, what about a design where we're gonna need via in pad? Well, at some point, the pitch on these BGAs becomes so small that we have no choice but to put a via directly in the pad. And that's because, of course, as we collapse the spacing between these pins, you will see here that there's not going to be any room for this via in between these pads. And so an example is shown here in one of our recent 1-minute design review submissions. Here in this design, they are using the NRF52 in the VFQFN package. It has a 0.5 millimeter vertical and horizontal pitch between these pins. And as you can see here, we have vias placed directly into the pad. Now, of course, if I were to try to put a via in this region, even with a 12 or 14 mil pad size, it just is not going to fit. You have no choice but to put it directly in the pad. Now, this is just for the BGA, but of course, we could do via in pad elsewhere in the design if we really wanted to. But in this particular design, you can see here that the rest of the components are not super high density. They're not super small components. We don't have a bunch of 0201s or 01005 passives on here. And so in that case, we don't have a requirement to put the vias in pad on the rest of the design. You can see here that we have one component right here, just a capacitor, where one of the vias is in the pad. That is acceptable because these vias in the fabrication notes for this design are going to be filled and capped. So because of that, it is still acceptable to put these vias in pad like you see here on this capacitor and like you see here underneath this NRF52 package. So now we've seen what kinds of designs might need via in pad, and we even see that you can use via in pad in cases where you don't necessarily have a high density BGA. But when you do have a high density BGA, there are of course reliability issues that can arise, and this has been studied pretty extensively by the IPC high density packaging user group, as well as PCB vendors and independent researchers. So let's take a look at some of that data right now. Now, the data that I'm showing in these slides has been presented in some other videos, and I'm going to link to some of these other videos in the video description. But for now, what I want to do is just kind of run through some of these BGA via in-pad defects that can arise during PCB assembly as well as after deployment in the field. So first, head and pillow is an assembly defect where you have incomplete wetting and soldering and fusion of these solder balls on the bottom side of the BGA, basically leaving a contact here between two separated balls of solder. And of course, that can lead to an intermittent short. Here, voiding occurs where you have voids that form in the solder ball, and you can even see here that we have some via in pad, where some of the solder does adhere to the copper pad on the PCB, but the void allows a crack to form along the bottom side of this ball, and then that also leads to an intermittent failure. Here you can also have a failure of the via in pad itself, where the cap essentially gets absorbed into the ball while the ball is molten, and that creates a failure of the via in pad. And then you can also just have ball fracture, where essentially you have repeated thermal cycling, the solder ball on the bottom side of the package gets fatigued, and then eventually a crack forms, and then you get a fracture. So with via in pad, when we have via in pad, we want to make sure that we prevent some of these defects. And one way to help prevent some of these defects is to ensure planarity of the pad arrangement in that BGA footprint. Now, planarity can get affected due to dimples in the via in pad plating over process. So when you have a via in pad, you then fill it and cap and plate it. The plating can form a dimple, and that dimple can then create some non-planarity. Now, on a small case passive, like for example, a 0603 capacitor or 0805, those kinds of passives, probably not a big deal. And on smaller BGAs with low pin count, Also, really not a big deal. But what if you have a really large BGA with 676 pins, like the example BGA that I showed earlier in the video? Well, in that type of BGA, that non-planarity can create a lot of distortion in the contact between all of the balls on the bottom side of the package and the pad in the PCB footprint. And that could potentially lead to some of the issues that we saw in the previous slide. So given all of these potential problems where you have a ball that could get fractured, or you have non-planarity leading to open circuits or leading to a head and pillow, things like this, what is the reliability of these different types of leadless packages where you can use via in pad? Well, the IPC High Density Packaging User Group has done some studies on via in pad in BGAs as well as QFNs. And so what I'm going to do now is show some reliability data for 3 different types of packages: a BGA 192 package, a ceramic BGA package, basically where the substrate of the BGA package is a ceramic material, and a QFN package on a 6-layer PCB. Now, the microvia aspect ratio on all of these packages is less than 1, which is going to be considered a highly reliable microvia. Now, these samples were thermally cycled, and then they looked at the failure rate in each of these different package types. So first, let's look at the reliability data for the QFN package compared to the ceramic BGA package. So here what you're seeing in these plots, these are Weibull plots, and we're comparing the lifetime of these microvias for cases where we have via in pad versus no via in pad. And what you're seeing here for the QFN is that the QFN package with via in pad has approximately a 12% shorter lifetime than the QFN package without via in pad. Now, eventually these two curves overlap and they have the same lifetime after you do enough thermal cycles, which is exactly what you would expect after repeated thermal cycling. Now take a look at the ceramic BGA package. The ceramic BGA package with no via in pad has similar lifetime as the ceramic BGA package with the via in pad. So I think this is a little surprising, because when we talk about reliability of via in pad, we might expect that the via in pad reliability doesn't really depend on the package type, and the data just shows that that isn't true. Next, let's compare the BGA 192 package with the ceramic BGA package. So again, the ceramic BGA package without the via in pad and with the via in pad have similar lifetimes, but when we compare the BGA 192 package with the via in pad versus BGA 192 without via in pad, we see very clearly that the BGA 192 package without via in pad has a 57% longer lifetime, significantly longer lifetime in this BGA package with no via in pad. So again, you can use via in pad if you like, but this is one of the risks that you run into. And using via in pad is going to give you different levels of reliability depending on the package that you're working with. So again, QFN is going to show a slightly lower lifetime, but with a BGA 192 package, which has an organic FR4 substrate, it is going to have a much lower lifetime than a ceramic BGA package. Some further data from the IPC High Density Packaging User Group shows a few important points. So number one, failures tend to most commonly arise near the corner balls in the BGA package. That actually makes perfect sense, because if you have any level of non-planarity that could be thermally induced or it's influenced by the presence of dimples in the via in pad process, you would expect that deformation to accrue over distance. And that's exactly why you would expect these failures to be more common in the corner balls of the package rather than in the center balls of the package. Now let's look at the data in the table in the bottom half of this slide. Here in this table, what they're looking at ultimately is the number of components that do not show voiding in the corner solder balls. And what you can see in the ceramic BGA package is that after thermal cycling, all of the components show voiding in the corner solder balls. So basically all of those solder balls are going to be at risk of failure from further thermal cycling. Now what about the BGA 192 package with via in pad and no via-in pad. Well, here you can see a very large difference between the via-in pad case versus the no via-in pad case. Only one of the components does not show voiding compared to 24 of the components showing no voiding, which means that the via-in pad component with the BGA 192 package shows many more failures. Now, what about a smaller BGA? For example, an 84-pin BGA with via-in pad versus no via-in pad. Well, again, the via-in pad package shows more failures, but still fewer failures than the larger BGA. And again, this is what we would expect with voiding that arises in the corner balls of the package. If you have a physically larger package, you're going to be at more risk of voiding and failure at the via-in pad because, again, that deformation accrues over distance. So that's exactly what the data shows us here. Now, reliability is clearly related to two things. Number one is the size of the package, and then number two is the materials used to make up the package. That's why we see the difference between the BGA 192 component and the ceramic BGA component. I guess there's a third part, which is what happens in the PCB design and then the precision of the PCB manufacturing process, but really the package matters as well. To help ensure reliability of BGA packages, PCB assemblers have done a really great job of planning their processes to ensure that the number of reflow cycles is minimized. Also, newer materials are available that have a closer coefficient of thermal expansion matched to the coefficient of thermal expansion for copper. So these newer materials are enabling much higher density packages and PCBs. Some of the material vendors are, for example, AGC. They produce a new resin-coated copper that has a low CTE, and Paul Cook, one of the podcast guests, was actually at a recent SMTA event on Ultra HDI talking about some of these materials. So I will probably have Paul back on the Altium On Track podcast to discuss this more, and I might even have a conversation with him on my channel. So make sure to subscribe to Altium Academy and this channel to stay tuned for that content. Thanks everybody for the awesome questions on this channel and on the Altium Academy channel. And of course, if you ask a great PCB design question, it's probably going to end up in one of these videos. Make sure to hit that like button, hit the subscribe button, and I'll see you next time, everybody.